Okay, welcome back. It's a great pleasure to welcome Mikhail Wolf, who's going to talk on quantum information channels.
Okay, thank you very much. Good morning, everybody. Let me first explicitly thank the organizers for giving me the opportunity to be here, despite the fact that I never ever worked on quantum control theory. And this is the reason why my topic is a little bit off topic, but hopefully nevertheless of help for some of you at some point. Yeah, so I promise to give some introductory or tutorial-like overview talk on quantum channels. Okay, and as you see, I will do this on a blackboard. So what's a quantum channel? Let me start very basic. So from a distant point of view, quantum theory is a very successful framework for computing probabilities in statistical experiments. Yeah, and for this we basically need two things. So we need a description of the measurement, which is usually some positive bounded operator, which we assign to a set of measurement outcomes. And we need a description of a preparation. Okay. In many cases, this is again given by a positive, but no trace class operator. Okay, this is not the most general scenario, but this is the scenario I want to consider. Yeah, and then. Well, then, given these two descriptions of measurement and preparation, quantum mechanics tells us how to compute probability by taking the product of those and the trace, and this is our Bond rule. Okay, so quantum channels come into play if you do something in between preparation and measurement. Yeah, so there's some black box, which is called T. Don't ask me why I call this T, maybe for time evolution. And this is my quantum channel. So now in order to be able to put this on the same footing again, there are two pictures. One is to put this T together with a preparation and to regard this as a new preparation. And this is what we know as the Schrödinger picture. And the other picture is to regard this entire thing as a new measurement, and this is the Heisenberg picture. Okay. So now let me a little bit more formally define what a quantum channel is, say first in the Schrödinger picture. Yeah, so a quantum channel in the Schrödinger picture, this is a bounded linear map from the set of say, trace class operators on one Hilbert space to the set of trace class operators to a different Hilbert space, which has two additional properties. So it's trace preserving, meaning that, well, it preserves the trace. Yeah, so for all trace class operators rho, this holds, and it's completely positive. Meaning that if I tenorize this map with the identity map on some n by n matrix algebra, then this is positive in the sense that it maps positive operators to positive operators, and I demand this for all n. Yeah, so this is positive in this sense for all n. Okay. So this is a quantum channel in the Schrödinger picture. In order to get the quantum channel or the description in the Heisenberg picture and this is sometimes called, maybe let me continue here, also the dual channel or the quantum channel in the Heisenberg picture. And this is obtained by imposing the following identity. Okay, so what we get is a map from B of H prime to B of H, defined via this relation. So for all rho in the trace class and all bounded operators on H prime. Yeah, so this is well and uniquely defined, basically due to the fact that B of H is isomorphic to the dual of the space of trace class operators. Okay. So now if we look at those properties, so of course we again obtain a linear map. It will again be completely positive, but the trace preserving property is now expressed and translated to unitality. Yeah, so the description of the channel in the Heisenberg picture will give rise to a unital. Yeah, so the trace preserving becomes unital, meaning that it maps the identity to the identity. Okay. Yes, true.
Maybe I missed in the beginning the preparation T measurements. So this is a physical channel, two separate systems, or the same system you're just describing the time evolution. When you say channel, is there a physical channel? Are you talking about state transfer?
I mean,
involved, or
yes, of course. There's an underlying physical process, and so in the end of the day, I mean, this is a very coarse-grained picture. Yeah, so usually we're interested in more fine-grained details of what happens here. We do not maybe we do not only want to have one black box description. Yeah, and of course, I mean, there might be several systems. This might be a composite system, and then the time evolution on this composite system. So this T might be just free time evolution, yeah, or this might be interaction with some environmental system, or whatever. Yeah. Okay, so far this is not specified, but these are the constraints, or these are the things which we have to impose on this map in order to be able to fit this into the standard framework of quantum theory. So these are the definitions, and now they're very useful representations of these maps. Okay, and probably the oldest one is the Steinspring representation, which states that, okay, let me take the Heisenberg picture. Like I can always express this in the following way. There's some ancillary Hilbert space and an isometry which goes from H to H prime tensor this ancillary Hilbert space. And provides us with a representation of the channel in the Heisenberg picture. Then another useful representation is the Krauss representation. Okay, so let me stay in the same picture. Where we have a sum of these so-called Krauss operators. And obtain a representation like this. The sum should be understood in the strong operator topology. And there's a relation between those two. Namely, the following. So if I pick an orthonormal system in the ancillary Hilbert space, so I is the ith basis vector then, take the tensor product of Vi, a Krauss operator, acting on psi, and take the sum over all of them, then this is equal to V, the isometry in a Stein spring representation acting on psi. So this is the relation between these two, and helps us to switch between these two representations. Okay. Then let me mention a last representation, which is used in the finite dimensional context a lot and very helpful as well. And this is the Choi and or Yamiokowski representation. Yeah, so now assume that we have a finite dimensional Hilbert spaces. Now then we can define a state vector which is called the maximal entangled one. And then we obtain a matrix which is called the Choi matrix or the Yamiokowski states, depending on how we normalize this. Which uniquely characterizes the channel by applying T tensor the identity. And the identity is now the identity on a D by D matrix algebra, where D is the dimension of H of our Hilbert space. So we apply this to a maximum entangled state, and this gives us a representation of this channel, which is in particular such that complete positivity of this map is reflected by positivity of this matrix. Okay. Maybe another relation between these three representations regarding the ranks or number of objects which appear here. Yeah, so in this, for the Stein spring representation, there's a smallest dilation space. Yeah, for the Krauss representation, there's a smallest number of Krauss operators. And for the Choi-Yamiokowski representation, there's the rank of this Choi-Yamiokowski matrix, and they are all equal. Yeah, so the rank of this Choi-Yamiokowski matrix, I mean, this is always bounded by the product of the dimension of these Hilbert spaces, and it's equal to the minimum number of Krauss operators, and it's equal to the dimension of the smallest dilation space in the Stein spring representation. Okay. If we choose this this ancillary space HE minimal, then this representation, the Stein string representation, this becomes essentially unique, where essentially means that the only freedom we have is a unitary acting on this ancillary Hilbert space. Okay. Now, there are many very useful and interesting inequalities which involve CP maps or quantum channels. And let me mention one of them, because this is a super simple corollary of the Stein string representation. This is a Schwartz type inequality. And the statement is that if I take a unital completely positive map, so with the star, I want to indicate that I'm in the Heisenberg picture, and I apply this to A star and to A, multiply this, and then the statement is that this is always in an operator order smaller than this applied to A star A.
The two stars mean two different things, right? For T star, it's defined as a dual channel, and A star is just the
Exactly.
Hermitian
Right?
Yes.
Yeah. So this is the. I mean, if you're allowed to put a dagger here. Okay. So this is a very simple consequence of the Stein string representation. Yeah. So let's, in order to see this, let's write out maybe the left side in terms of the Stein string representation. Then what we get is V star or V dagger, if you like. Okay, so that I just copied this twice. And now we have that V is an isometry. Yeah, so what does this mean? This means that this is certainly bounded by the identity. Yeah, so we can upper bound this by upper bound this expression by replacing this by the identity. But if we do this, then we get the Stein string representation of what we have on the right-hand side. Okay. There are many variants of this inequality. I think they were studied by people like Davis, Caddison, and Choi, and others. Let me mention one or two of them. So one variant of this inequality is one for positive and unital maps. So in general, this is not true for positive maps. But if A is normal, yeah, so can be diagonalized with respect to a unitary, then this holds for positive maps as well. And one way to see this is to argue that if A is normal, then all the arguments which we see here are elements of a abelian C-star algebra. And then we have a positive map on an abelian C-star algebra, and this can always be extended to a completely positive map. And for completely positive maps, we know that this is true. Okay. A second variant of this inequality which I think is due to Hansen and Pedersen, is the following statement. So if we have a positive map and we look at so now suppose that A is positive or positive semi-definite, And P, yeah, so P would be 2 down here, but now we can choose this between 1 and 2, and then this is still valid for every positive unitary map. Yeah, in fact, we can further generalize this, because the only thing the essential thing which we need in order to prove this is the fact that that the function which maps x to the power of p is operator convex in this interval. Yeah, so we could replace this by another operator convex function, and the inequality would still be true. Okay.
Sorry, you're saying that holds for all positive, not just completely positive?
This holds for all positive, yeah.
And do you need A to be normal, or it's true?
I mean, A is positive, so it's in particular normal.
Yeah. Sorry.
Exactly. Okay. Okay, so this is one simple but useful inequality which I may use later, depending on how much time I will have. Now let me discuss spectral properties of those channels, which in particular means that now we have to identify these two Hilbert spaces. So we have to assume that H prime and H are isomorphic or are equal, because we need an endomorphism in order to get a spectrum. Yeah, so spectral properties. Of quantum channels. Okay, so the first and simplest question you might ask is, where is the spectrum? Or even simpler, what's the spectral radius? Okay, so the spectral radius, this is the take the supremum over the absolute values of all elements in the spectrum. Okay, and one way to compute this is to exploit a formula by Gelfand, which states that in arbitrary Banach algebras we have that the spectral radius can be obtained by looking at the norm. So considering the norm of t to the n, and the nth root of this norm, if we take the limit n going to infinity, then this gives us the spectral radius. Okay, in order to compute this, we may use a result by Rousseau and Dye on CP maps, which states that the norm is equal to this is the operator norm. Is equal to the operator norm of this map acting on the identity. But now if this is unital, then we know what this is. This is 1. So we know that the spectral radius is equal to 1. Let me maybe. Okay, and we also know that 1 is part of the spectrum, because T star maps the identity to the identity. Yeah, so we have an eigenvalue 1. So this is not only the spectral radius, this is part of the spectrum. Let me maybe give an alternative proof based on a different norm, which, however, only works in the finite dimensional case. Because in the finite dimensional case, we can consider p norms. And then look at the P to P norm of our channel, and what one can show is that this is always upper bounded by the dimension to the power of 1 minus 1 over P. Okay, but if the dimension is finite, then this is some number, and this is a bound not only for T but also for T to the n, because T to the n is also a channel, and this to the power of 1 over n with n going to infinity is 1. Yeah?
So the T star is always unital, but the T itself might not be unital.
No.
So
why
that
so if I do not say anything else, then T is trace preserving and T star is unital.
So why that thing is equal to 1 then? Then you use the result from the T star. Is the norm the same?
I mean, you can express this in terms of T.
Okay.
Yeah. So you have to basically replace the operator by the trace norm when you go to the dual. Okay. Why did I want to say this? Because so in the finite dimension case, since T is a linear map, so it's an endomorphism in this case, we can not only assign eigenvalues to this, we can also assign singular value to this. Yeah, and the singular values, or the maximal singular value, is the 2 to 2 norm. Yeah, so what we learn here is that although all eigenvalues lie in the unit disk, the singular values, they can be much larger. Yeah? I mean, this is sharp, so there are channels which have singular values, square root of t. And one can show that this is equal to 1 if and only if, and this is a little bit referring to the question, if t is unitive. Or then doubly stochastic, because then it's trace preserving and unitive. And then the singular values are also bounded by 1. And this is an if and only if. Okay. I need another blackboard.
How exactly is the sorry, the norm for the channels defined? The norm of T? Is this just considering operators as vectors and taking the operator norm?
Yes, I mean it depends on. So like if you take this P to P and you so this would be the P to P norm, or the P to Q, where you replace this by Q.
Okay. And the one in the Russo-Die result, that the norm of T star.
Well, the P is, this corresponds to P in infinity, so this is
yeah.
in this case, and you take the operator norm. So one further very simple result is, very simple property of the spectrum is that it's closed with respect to complex conjugation. Yeah, so whenever I have a lambda in spectrum of T, then lambda complex conjugate is also in the spectrum. Yeah, so I mean this is easy to see. So suppose that lambda is indeed an eigenvalue, but it also works for other elements in the spectrum which are not eigenvalues. But suppose it's an eigenvalue, then we have that. Okay, so we assume that this holds true. And then by taking the adjoint of this equation, so what we get is, since T is completely positive, so in particular hermeticity preserving, you obtain this equation. Yeah, so lambda complex conjugate is also in the spectrum. Okay, so these two things taken together have a very simple consequence. Yeah, maybe. Yeah. So let me from now on let me stick to the finite dimensional case. Okay, the consequence for the determinant of the channel. Yeah, so we have that all eigenvalues are in the unit disk, and they're either real or they come in complex conjugate pairs. So this means since the product of all those is the determinant, this product is real, and it's in between plus and minus 1. Okay. And one can show that minus 1 can never be achieved. It can be achieved for positive maps because the matrix transposition has determinant minus 1 in certain dimensions, but not for CP maps. And for CP maps, one can show further that the determinant is 1 if and only if this corresponds to a unitary evolution. Yeah? So in the Krauss representation, there's only one Krauss operator, and this is a unitary. Okay. So this has a very in my eyes funny consequence. So regarding the semigroup structure of the set of quantum channels. So this implies basically that there are indivisible quantum channels. Yeah? So it's clear that if we compose two quantum channels, then we get again a quantum channel. And now, for some reason, we might ask the converse question. So given this black box, so can we decompose this into smaller pieces? Yeah, so is this quantum channel, can this be written as a composition of two quantum channels? Yeah, and maybe we want to continue this and eventually represent this as a continuous time process. Okay, but now a consequence of this is that there are quantum channels where this is not possible. Yeah, so it's not possible to decompose this in a non-trivial way even into two other quantum channels. Okay. Well, we have to rule out one case, because what is always possible, so we can always do the following. So if this is T, we can always find a composition like this. T, a unitary, sorry, you cannot read this, and the unitary inverse. This is a trivial, I mean, this is cheating. This is not really decomposing this into smaller building blocks. Okay. And this corollary states that there exists cases where this is the only way of decomposing a quantum channel. So let me define the following. So some calligraphic T, which is the set of all quantum channels in the Schrödinger picture, maybe acting on the d by d matrices. And the statement is that there exists a channel such that for all pairs of channels whose composition is equal to T, we have that at least one of them has to be a unitary. Okay, meaning, loosely speaking, that we cannot decompose this channel at all into smaller pieces. Yes?
Because when we, I mean, this must have implication when we decide a channel is degradable or antidegradable, because there we are composing two channels. Yeah, so if you, but there, you know, unitary, right? If you look at the complementary channel when acted on, composed with another channel.
Well, of course. I mean, of course, they are. In fact, this is the generic case. I mean, there are cases where you can decompose a channel into smaller building blocks in a non-trivial way.
Yeah.
Yeah. Like if you have a continuous one-parameter semigroup, then you can continue this forever until you are left with a continuous time process. But the only thing I want to state here is that there exist examples for which you cannot do this at all.
All right.
Yeah. And the proof is very simple by looking at the determinant. So take T such that the determinant of T is equal to the minimum which turns out to be negative. Yeah, so this is, take the channel which has the smallest determinant. I mean, everything is compact, so there's a channel which has the smallest determinant. Yeah, and we could easily construct channels with negative determinants, so the smallest determinant has to be negative as well. And then for this channel, we use that, of course, the determinant is multiplicative. Yeah, so if this channel is composed of T1 and T2 in this way, but now the determinant is bounded between plus and minus 1. So if this has the smallest negative, the most negative determinant, then one of them has to have determinant 1, because if it would be smaller than 1, then the other would have to have even more negative determinant. Yeah. Okay, and then one of them has to be a unitary. Okay.
How close you can get to -1? Does it depend on the dimension?
Yes, in principle I should know, but I don't know. I don't remember this off the top of my head because I never found this very important.
So these channels with minimal determinants, they are well characterized.
Yes. Okay, so I can give you the channel in dimension 2, and in dimension 2, this is the best approximation to matrix transposition. Yeah, so the matrix transposition is not a CP map, yeah, but within the set of CP maps, you can approximate matrix transposition, and the best approximation will have the smallest determinant. Yeah, and this is, I know, -1 over d plus 1, maybe, I have no idea. No? I don't know. Yeah, maybe something like this. Okay. So what have we learned so far? So we have learned that the spectrum is in the closed unit disk. There's always an eigenvalue 1, and the eigenvalues, they come either in complex conjugate pairs or they are real. Yeah, so this is how the spectrum looks like. Apart from this, there are no further constraints on the location of any single eigenvalue. Yeah, so if you give me any point in this closed unit disk, then I can give you a qubit channel which has this point as an eigenvalue. There's no further constraint. This is in contrast to the classical case. Yeah, so the properties which I discussed so far also holds for stochastic matrices. Yeah, so they also have the spectral radius and all the other properties I discussed so far. However, in the classical case, there are further constraints on the location of single eigenvalues which depend on the dimension, and we can only get the entire unit disk if we go if you let the dimension go to infinity. Okay.
You have no constraint inside the disk, but on the circle you have constraints.
No. Not for the location of a single eigenvalue. Okay. Yeah. Okay. So these, of course, the spectrum is not something which is directly observable. So it's not that you look at a system like in an experiment and then you see the spectrum, but of course it influences what you observe. And one way or one way to, let's say, indirectly see the effect of a spectrum is to look at a time series which comes from the evolution of an observable. Yeah, so let's say AT, say this is the so suppose this, our channel describes the time evolution of a system for 1 unit in time. Yeah? And then we look at the time evolution of the expectation value of an observable for various times. But now this is, of course, this is discrete, so t is a natural number. So there's some time series which we may observe.
It's
and
not
then,
10 power t. It's not 10 power t.
no, it's just
t.
to the power t. So one unit in time, 2 units in time. Yeah. So we, of course, there's an assumption underlying that we have this Markovian time evolution. Yeah, but suppose that this is the case. Then, if you look at the discrete Laplace transform or the set transform of this time series, so let's do the following. Okay, so this defines a meromorphic function on the entire complex plane, and it turns out that the poles of this function are the eigenvalues of the channel. Okay. Let me bring this together with what I said before. So it's not difficult to show that whatever time series I have, I can express this in this way or in the analogous classical way, where this is a classical stochastic matrix. So from this time series, I cannot distinguish the quantum and the classical from each other. However, there might be an enormous difference with respect to the dimension I need for this representation. Yeah, because if I have a pole at some place, I don't know, in the unit disk, which is classically only achievable in the limit dimension going to infinity, yeah, then this might be representable, or this is representable in the quantum case, even by a qubit evolution. Yeah, so there's no, yeah.
What's the intuition behind this? Is like the phases tend to go everywhere, or I mean, behind the fact that quantum goes everywhere.
Yes, I mean, of course, exactly. So the problem for the classic description are the phases. Yeah. So if you take something on the boundary, then you are in trouble if you choose this appropriately. Okay. So this. Okay, maybe so this were the elementary properties of the spectrum. Let me first answer your question, then come to something
Can we
more
learn
sophisticated.
something from this type of analysis about the uniqueness of the steady state of the system when the time goes to infinity state?
Let me. No, it's not. Let me come to this in 5 minutes, maybe, hopefully. But okay, let me first tell you something about more complicated constraints. Yeah, so I said that in a quantum case, there's no further constraint on the location of a single eigenvalue. But if we regard the set of eigenvalues as a multiset, then there are constraints. Yeah, so if we fix some of them, then the other eigenvalues, they cannot lie everywhere. And this, so what we know about this can be basically summarized like this. Okay, so suppose that this is the spectrum, but now the spectrum as a multiset, meaning that I take care of multiplicities. Yeah, so an eigenvalue can appear there several times if it has higher multiplicity. Then one can show that the moments of this multiset of eigenvalues, meaning that so if I take each of them to the power of some k, some natural number, I sum over all of them, this is always positive for any k. And conversely, if this multiset contains 1, and otherwise only numbers whose absolute value is smaller than 1, and this is satisfied, then we know that there exists a channel such that it's the non-zero part of the spectrum is the non-zero part of lambda. Yeah, so the spectrum of t without 0 is lambda without 0. Okay, so we have to exclude the 0 because, of course, these moments, they do not see 0 eigenvalues. Yeah, so we can add arbitrary many zero eigenvalues in these moments that would not change.
The n is the same as the. Yeah.
No. No, because of the zeros. Yeah, so these are only the non-zero eigenvalues, and there might be a large number of 0 eigenvalues, and this might be necessary for this representation. Yeah, and this is somehow, I mean, this is what we do not understand at all. So how large does the kernel of this channel have to be such that it can have this spectrum? This could be unbounded, but this is something we don't know.
There's no functional relation.
We don't know.
No.
I don't know. Okay. One last blackboard. So let me now move into the direction of the question about stationary states and okay, maybe convergence. So we know that, I mean, since there's always this eigenvalue 1, there exists at least one stationary state in the Schrödinger picture, or at least one conserved observable in the Heisenberg picture. Again, this conserved observable may just be the trace or the identity. But there might be more. And if there are more, then they have a very nice structure. So let me formulate like this, as follows. So we have, suppose there's a positive definite stationary state. I'm not supposing that this has to be unique, just there exists one which is positive definite. Then the set of, say, conserved observables, so all x all fixed points of the channel in the Heisenberg picture, then this is a star algebra. Yeah, so this means it has a very nice structure. You know, since in the finite dimensional context, the every star algebra is basically a direct sum of matrix algebras. Okay, and this has a very simple proof, and this is one of the reasons why I told you about the Schwarz inequality. Okay, so what's a star algebra? So a star algebra is, of course, it's a vector space. Yeah, but that this is a vector space is trivial because T is linear. Yeah, so of course we get a vector space. It's closed with respect to taking the adjoint. This is also essentially trivial. So what is not obvious is that this set is closed with respect to taking products. Yeah, so if one observable or one element in here, there's also, or let's say 2 elements in here, that the product of those 2 is also in there. This is what we have to show. And by the usual polarization tricks, it's sufficient to show that if A is in the set, that, say, AA star is in this set. Yeah? So if you know this, then by replacing A by linear combinations of other elements in here, then we get also that products of different elements are in there. Okay, but this is the thing which we have to show, and this is done in one line from the Schwarz inequality. So what we want to show is that if A is a conserved, so if A is conserved in this sense, that this is 0. Yeah. But now, by assumption, this is T of A star. Yeah. So what we have here is the expression which appears in the Schwarz inequality. So we know for sure that this is positive. Okay, but we want to argue that it is 0. Yeah? So, and for that, we take the trace with our stationary state. So we take the trace with rho. If we do this, and we let this T act on rho, then we get that this trace is 0. And now we have the trace of a product of positive operators, which is one of which is positive definite by assumption. Yeah, so the other one has to be 0. Yeah, and then this has to be a fixed point. Yeah, so the set of fixed points is a star algebra. So from this, one can, for instance, also conclude that if we now look at the set of fixed points in the Schrödinger picture, so the set of stationary states, or the space spanned by those stationary states, that this is a star algebra as well, without further assumption. Yeah. The only difference is that in the Schrödinger picture, this becomes a star algebra with respect to a modified product. Yeah, so here we take the ordinary product between the matrices, or between these operators, and in the Schrödinger picture, we also get a star algebra, but we may have to modify the product.
So what is the statement in the Schrödinger picture?
That it's always a star algebra with respect to a modified product. Yeah, and this I know is sandwiching with the inverse square roots of the or with the square roots of the fixed points with maximal rank, something I can with.
Does that product have any physical meaning, or the product of states?
Okay, I don't know. I don't know. So what else? Okay, so this is about the structure of stationary states or of fixed points in either Schrödinger or Heisenberg picture. Now, having many fixed points is something which generically does not happen. Yeah, so the generic case is that this eigenvalue is non-degenerate and that the stationary state corresponding to this is faithful, so has full rank. This is what happens generically.
Generic with respect to what measure?
Whatever. So it's a dense, open, path-connected set which has this property. Okay. In this situation, so this can be characterized in many different ways. And this is maybe the last thing which I want to do. Okay, so having only one eigenvalue of magnitude 1 and is equivalent to saying that if we look at the long time evolution governed by this map, that this long time evolution converges to the stationary state. Yeah, so this is what happens generically, and this can be expressed in various different ways. So one way is in terms of, let's say, the Choi matrix. So there exists an M such that the Choi matrix of T to the M is positive definite. Yeah? These two statements are equivalent. We can also express this in terms of the Krauss operators. So there exists an M such that the span, so that the complex linear span of all monomials of Krauss operators of order M, this is the entire matrix algebra. Yeah, this is also equivalent. And another equivalent statement is that there exists an M such that T to the M applied to a pure state is positive definite for all non-zero psi. Okay, so all these are equivalent, and one can show that this M can be chosen d to the 4. Yeah, so if one and therefore all of those statements are true, then we can choose M equal to d to the 4. I think I should stop here. Okay. Thanks a lot for your attention.
We have time for 1 or 2 questions.
So it may be a stupid question, but what is if the psi is the fixed point of T, or you're excluding that here?
If psi is the fixed point, then none of those statements is true.
It can't be a pure state.
So what what I say is that if one of those statements is true, then all of them are true. Yeah, and this in particular implies
sorry, I
that
didn't
the
see.
pure
Okay,
state.
rho is larger than 0. Okay, sorry. You're only considering convergence to some positive state.
I mean, so I'm making the statement that all those statements are equivalent, and this in particular implies that there cannot be a pure or non-faithful fixed point of T. And this is the generic case. So the set of channels which fulfills this, and this, and this. This is dense. This is open. This is path connected. This has full measure everything. Okay.
Okay.
Can I ask one?
Narendra?
And from the information theory point of view, when we're talking about channels, we're interested in things like capacity and stuff like that. So these beautiful properties, will that shed any light on